Great. So let me just share the screen for the recording. And move myself off there. Okay, so today we're going to talk about sensitivity analysis. Sensitivity. I was just saying, so it's in most European languages, the word sensible means sensitive in English, and it used to mean sensitive in English, and somehow it shifted. So it's quite confusing when someone says, I'm going to do a, that measurement isn't very sensible, and what they mean is sensitive. And you get that confusion a lot when you're speaking to people in other languages. So it would often be sensibility analysis in other languages, but sensitivity analysis, which is all about how simulations might respond to their inputs. So we've got different inputs and we expect the output of the simulation to be different as we change them. And we're going to do it in the context of EmuKit, and you've got a lab class as ever where you've got some tasks to do with sensitivity analysis. And I think it's almost like the first thing that you might want to do if you have a surrogate model or an emulation in the real world to better understand the simulation you're working with. So I like this, there's a book on sensitivity analysis, which, the whole book is about it, and we're only going to do one lecture on it, but this is a definition from that book. Possible definition of sensitivity analysis is the following: the study of how uncertainty in the output of a model, numerical or otherwise, can be apportioned to different sources of uncertainty in the model input. A related practice is uncertainty analysis, which focuses rather on quantifying uncertainty in model output. Ideally, uncertainty and sensitivity analysis should be run in tandem, with uncertainty analysis preceding in the current practice, right? So it's the difference between uncertainty and sensitivity. Sensitivity is a sort of characteristic of the simulation, right? Whereas uncertainty is not necessary, it's how unfamiliar you are with it. Now, you'll see local sensitivity come up a lot. So if we've got a linear model, what we're talking about here is very easy, and that's why people like to use linear model, particularly in statistics, because the sensitivity of the output is just equal to the sort of the coefficient. So local sensitivity, so if we've got a function that is a simulator of some form, and we were operating around a certain point, we can see the local sensitivity is just the gradient of the function at any given place. And you'll see, for example, in machine learning, where people are trying to explain the output of a neural network, you'll quite often see the gradients of the output with respect to the inputs being used. So that's a common and relatively straightforward thing to do, particularly with automatic differentiation. It's also something that I would see a lot in the Amazon context, where people wanted to look at an operating point, and they wanted to understand why the predictions didn't match what happened in reality. And they would very often linearize the operating point. So they sort of look at the system, they fit a linear model around the point that you were operating, and then you explain to the vice president what went on by looking at the coefficients of the linear model. You sort of say, oh, it turns out in practice that the variation that we saw between what we predicted to happen, what actually happened, was 30% due to our suppliers under-delivering on the stock, 20% due to our demand predictions being too low, and 5% due to whatever the other factors you're considering. So that's relatively straightforward, and we're not going to talk too much about that in this lecture. What we're going to be looking at more is so-called sort of global sensitivity analysis. So imagine we have a domain over which we expect our function to be operating, and we're interested in what the sensitivity of that function is across the domain. So here, we're representing that domain of inputs as a probability distribution over X. So we can think in general that the certain inputs we might expect to see sort of the likely operating positions of the function, P of X. And we've got our function itself, G of X. And we want to sort of express the variation in range. So we look at the variance of G of X, where the expectations are defined under P of X. And I should be clear, sorry, I habitually use these angled brackets for expectations. It's something that comes from physics. And the reason I like it is because you can sort of so you might write this with a funny E, right? The expectation of G of X squared. but I habitually use these angle brackets, and this is the definition here. It's just saying the integral of whatever the function is inside the brackets there underneath P of X, right? And it's a sort of physics thing because it's quicker to write the expectation. And I like the fact that you can then put as a subscript the distribution you're taking the expectation under. It's slightly odd, actually, when you look at expectations in many literature. They never tell you what you're taking the expectation under in the notation. It's always implicit. They just put the E of something, which I find slightly odd because as you start trying to do things in emulation and simulation, then what you find is sorry, I'm just suddenly thinking, am I actually recording? Yes, I am recording, good. It's weird how those things pop into your head as you're saying expectation. So it's the sort of thing that when you're doing this type of work, you actually quite often want to be clear what you're taking the expectation under. Because here it's the prior distribution over which we expect things to run. But you could imagine doing a bit of localized sensitivity analysis, can't you? You could imagine saying, instead of doing that expansion around the operating point, you could say, why don't I look at the expectation around an operating point and use a different expectation here than the one I'm talking about up front. But the key point is that you're sort of interested in the variation of the outputs as a function of the variation of the inputs. And this is the sort of equation that you care about. Okay. So what we're going to do is we're going to make an assumption, and this could be very often incorrect in practice, that the input density factorizes, right? This is going to become not the sort of thing happens as dimensions of inputs gets larger. In high dimensions, it's quite rare that you would see like total uniform factorized distributions like this is implying. So here we're sort of saying, oh, each dimension X is sampled from a uniform distribution. We can just scale it to be between 0 and 1. So that's sort of general. So we're just saying the bounds of this thing is between 0 and 1. And then we're saying that across, to get the multivariate dimension, that we're just assuming independence across those different dimensions. So in effect, we're creating a square of inputs. And we're saying that inputs to this system are uniform across that square. In practice, that's very often not going to be the case because some of these inputs will relate to each other. So there'll be correlations amongst them, and they won't totally fill the space of inputs that we might be interested in. But for the moment, we'll just assume this for all the analysis that you're going to do. Now, this is the fun bit. So there's this wonderful decomposition, which is an orthogonal decomposition that underpins the sensitivity analysis we're going to care about. And this is the decomposition. So it's of the form that you decide that your function can be decomposed into these components. So g of x is equal to g of 0, which is not dependent on anything. So it's a sort of a constant. Plus, it's equal to a sum of terms where each term is only dependent on one input. Now, if this was a linear function, we could stop there because there's no interaction between the terms, right? But here, what we do is we go forward and we say plus a set of terms that look at the interactions between each input, right? So here, this is the sort of two component interactions. So this is saying, so actually a quadratic function has these terms right in, but wouldn't have anything higher order. So these are becoming higher order terms. So the sort of third term here is functions of two variables, yeah? So how these input variables are interacting. Now, in order to get the whole function in general, you actually have to keep going. So functions of 3 variables, functions of 4 variables, all the way up to a final sort of residual value. So it's almost, you can think of these like residuals. What you're trying to do here is like, I'm going to decompose my function. I'm going to take away the behavior of the function, which is associated with no input. And then I'm going to, so think about like subtracting, right? What are you left with? So g of x minus g of 0 is equal to all these terms, right? G of x minus g of 0 minus the sum of the individual terms is now equal to the remaining terms, which are the sort of second order interactions, the third order interactions, the fourth order interactions, all the way up to the pth order interactions, right? And so this is called the Hofding-Sobel decomposition, and it underpins the nature of global sensitivity analysis. It's a very weird effect where I think the light on your phone is on and it's reflecting right into my eyes. Thanks, Kush. Great. I'm very sensitive to people with bike lights that point up as well. I get really grumpy. Put your light down. So I try not to be grumpy, but thanks, Kush. So there's it's a decomposition of the function into those terms. So you can see what we're going to try and do here is we're going to look at the sensitivity to these different terms, the sensitivity to one term overall, and then the interaction terms. So as I say, if this is a linear model, basically everything above this point disappears, right? And very often what we do to try and explain what's going on in a system is we linearize it around an operating point, and then that's just the first 2 points. But in general, all of these terms exist. So what do we care about? Well, we care about expectations under these terms. So if we start sort of decomposing each of these terms here, we can start seeing how they're formed. So it turns out that G of 0 is just the average of everything, right? So as we want to know what each of these terms are, G of 0 is the average of all terms. But okay, watch this, because this is sort of key. You've got to do these things in this residual way. If you now want to know what G of Ix is, then you have to look at the average under all of X apart from the ith term you're interested in, right? So you're subtracting off. So G of Ix, you've already tried to explain with that, so you have to put that on this side. And now what you're trying to do is integrate over every term apart from the term you're interested in. So my P of X not I is basically, oh, is that right? I got that right? It's integral of everything apart from I. I've done that one wrong, haven't I? Yeah, that's incorrect there. My P of X not I is the distribution over the inputs for everything apart from the ith one. There's a missing, I think that, and ignore that bit there. I can't think live about it anymore. That's a weird thing, and you know this stuff, but you can't think live. But this one here is sort of giving you the basic point. So integrate across all X apart from I, and then you're left with a Xi, and you're left with a Gi of Xi. That leaves you with a function of Xi. You've marginalized everything else out, and then you subtract off the G0 and do that for every one. And then you just repeat this process. Okay, now we're integrating over everything apart from X, I, and J, subtracting off all the relevant Xis and Xjs, and so on. Yeah, so it's defined recursively in order to how to get these things, this Hofding-Sobel distribution. But what we actually care about is the variance, right? And so the variance of these, so what we want to do is decompose the variance of the output into some form which gives us the variance of the inputs. And if we start writing all that down and do a lot of maths of multiplying everything out, what you start finding is you get these variance decompositions. Now, variance decompositions are very, very, very common. You'll see them all over the place because variances are additive. It's a sort of slightly, I don't know, I used to get confused about this when I first studied Gaussians, because like, it's weird, isn't it? Because sort of standard deviations exist on the real line, don't they? So you sort of think, well, I've got two variables and I add them together and they both got a certain standard deviation. You might think that the standard deviation of the new system is the sum of the standard deviations, because that works out nicely. But that's not true. If that were true, then like various effects in real life that we observe wouldn't happen, like the fact that actually as we add observations, we tend to get a reduction in noise. And the reason why we get a reduction in noise is because it's the variance that's additive, not the standard deviation. So if you want the standard deviation of the new system, we're adding two functions together, we add the variances together and take the square root. So instead of like standard deviation plus standard deviation, it's square of standard deviation plus square of standard deviation square rooted. Yeah, because variances are additive, not standard deviations. And so that you project back to the real line with the square root term. So the fact that variance is additive is everywhere in machine learning, correlation, and all the time. And the fact it's so common that people even don't normally point it out. And this decomposition, then you get the same thing. You get these additive terms as you try and multiply everything out. If you're looking at the variance of the output, Of course, the G0 term disappears because it's a mean and it's got no expectation on it. So when you're taking the expectation, the G0 squared here minus G0 squared happens, and you end up with this decomposition in terms of the sum of variances. And that's what you study when you're doing sensitivity analysis. Indeed, well, you take it a little bit further because you can always look at the total variance of the system. And so the Sobel indices are defined for any of these order terms as the variance associated with those terms divided by the total variance. So that means that they sum to 1 because this thing here, this total variance, look, it's the sum of each of these terms. Like these are the individual terms. Here's the second order terms all the way up to the pth order terms. So the total variance is the sum of all of them. And so the Sobel indices are then defined by dividing by the total variance, and then you get an index, which is telling you what proportion of the variance each of these terms gives you. So if you do your sort of sensitivity analysis and you compute the Sobel index, which is what you're going to do for the first input, and it comes out as 1, you know that no other input is having any influence because you've saturated the Sobel indices, right? So that's the reason for dividing by the total variance. And then that gives you a sense, you can talk about relatively which of your inputs is the one that is giving you the outputs at the end, right? And you can make judgments about how sensible that is. So here's an example. This is quite a commonly used example because you can compute the Sobel indices for this analytically. You can compute those terms because it's sort of just formed in a relatively simple way. So it's known as the Isogami function. And it has these sort of interactions between x3 and x1. Yeah, so it's in x1 and x2, it's got these terms here, but then it's got this sort of interaction term between x3 and x1. So here below is the decomposition. So these are the non-zero Sobel components of the Isogami function. So these are the things. So there's a component that's associated with x1 and x3, which is coming from there. There's a component that's associated with x1 and a component associated with x2. There is not a Sobel component associated with interactions between x2 and x1 or x2 and x3 because there are no such interactions in the function. Yeah. Now, we can see that here because it's a function that we've defined, like a lot of the things we're doing. The notion is that if you were running a large simulation, and you didn't write that simulate, well, and even if you wrote that simulation, you wouldn't necessarily know how these terms are interacting. So here, of course, we can see it. And then in the experiment in the lab class, you'll simply go through that. So in the lab class, what you'll see is how to compute these different indices. But more importantly, what you do is you're going to do it by emulation as well as running the real function. So of course I can compute these indices. What we're going to have to do is work out these variations. But in order to do these variations, I have to sample, right? I have to do Monte Carlo sampling again in order to compute these different indices. But now I have two options. I can either Monte Carlo sample on the original system, the simulation that's going to take a long time, or I can do Monte Carlo sampling on the emulation, which is going to be quicker. So in the lab class, that's exactly what you're going to do. You're going to sort of compare what happens if I look at the original function. Well, you know the true ones in these cases, but you can also do Monte Carlo. So I should step back a bit from what I just said there. So in this plot, what you're seeing that you'll recreate in the lab class, this is the analytic Sobel indices that we know because we know the function. We can write them down in this case. And then you're just going to do some sampling to estimate them, right? So when it comes to computing, I should have made that clear when we had the expectations up. These expectations that you need, they're not analytic, right, in general. So what you do is you estimate them by Monte Carlo, yeah? And once you've estimated them by Monte Carlo, you have to recursively estimate what the indices are. But as well as them doing by Monte Carlo, as you're doing here, where you're just putting the Monte Carlo through the simulation, So these estimates are, I'm just doing Monte Carlo through the simulation. I've done a number of Monte Carlo simulations. You'll then also say, well, what happens if I fit an emulator and then estimate the Sobel indices on the emulator? And then you get a Monte Carlo estimation plus a sort of uncertainty about what that estimation should be. So you can sort of see in this case, this the Sobel indices, the one for X3 on its own is 0, and for X1 and X2, they're non-zero. And there's the Monte Carlo estimates, which aren't quite right because there are obviously some stochastic noise there. And then here's the total effects. So, right, yes, that's the other thing you can do, is estimate the total effect of that variable. So the total effect in the Isogami function is not the effect of that function on its own, but the effect of all the terms that that variable is involved in. So when we look at this decomposition in the first place, you can see that there is no single non-interactive term of X3, right? So X3 is never on its own operating independently of the others. It only comes in with an interaction term. So the Sobel index of X3 on its own is 0 because it only operates in tandem with X1. But you're interested in more than that. What's the overall influence of X3? And that's the total effect. So that's the sum of all the indices with which X3 is influencing things. And in that case, because X3 has an interaction with X1, you see an effect on the total effect of X3, even though you don't see anything on the first order Sobel index for that variable. So this is kind of interesting because you see these sort of things that happen that wouldn't happen if you just do a linear approximation. You wouldn't necessarily pick them out or decompose them in that way. And you can start making decisions about the sensitivity on that basis. So obviously, actually, one of the effects you get is that as the Monte Carlo samples are in higher dimensions, which they implicitly are to compute these indices. So for this index, you only have to do a one-dimensional Monte Carlo sample, so one-dimensional integral. But as you go up to these indices, you've done up to a three-dimensional Monte Carlo integral in order to estimate them, and they start becoming less accurate. So how do you deal with that? Well, you try and take more Monte Carlo samples, right? So more and more Monte Carlo samples from the system. But if your simulation is slow, that's going to be really, really slow. So that's where emulation comes in. And the other thing that you'll do in the lab class here is do a GP Monte Carlo. So in the GP Monte Carlo, what you do is you're fitting your emulator to the simulator, and you run the Monte Carlo on the Gaussian process. Now, once again, like so many of our examples, computing the Gaussian process is actually slower than computing the user function in this case, yeah, because the user function is just a couple of signs being added together. But in general, that won't be true. And so the notion of what you're doing here is you're sort of trying to fit the Gaussian process to the simulator as a whole, then you're doing your Monte Carlo on the Gaussian process. And you can also, in this case, compute the variances of that Monte Carlo sample to see whether you think it's likely to be within the right regime. So here you can see it's not too bad in these cases, but in this case, it's actually quite a lot worse than the original simulation. And there's the total effects as well. So again, you sort of actually it's slightly better in each of these cases than the direct Monte Carlo. So I want to make sure we got sort of time for sort of questions about everything we're doing so far and anything you've done with them. Have people been doing the lab? This is one thing I suddenly started thinking. Are you actually doing all the sort of lab classes that we've set? Because they're all linked away, but we don't have special sessions. So people are. Who's done all the labs? Come on, no one. Okay, so I really advise that you do, because unless you do, you won't know what to do when it comes to your coursework, right? Because when your coursework starts coming, you're going to have to make decisions about what type of analyses that you use, right? So I suggest you look quite carefully at each of the labs as we provided it, because they're quite detailed and they're getting you right the way through Bayesian optimization and everything else. We sort of treat you as adults rather than sort of make sure you've gone through them. But it will make your conversations about what project to choose, which is what's about to happen, and which analysis techniques to choose much harder if you haven't gone through these sort of introductory sections. So in the lab class from today, this is Nicolas Durand, and Nicolas was a postdoc with me in Sheffield, but he also worked with Tony O'Hagan and Jeremy Oakley, who are real sort of experts in surrogate modeling in Sheffield. And he then went to the École des Mines in Saint-Étienne in France, where they have really interesting groups doing this stuff. And this whole sort of, in France, there's a really great community that does this uncertainty quantification that really bridges from quite very sophisticated mathematical understanding all the way through to an interest in the applications, serious engineering design applications. I reviewed a PhD once there and attended a meeting, and I always remember one of the applications was like modeling for Renault, their bumper design, their crush design, and they're sort of integrating surrogate modeling in that type of modeling. It's a really interesting community because they're also very good at speaking the different languages of the statisticians, because the techniques we're talking about are used by statisticians, machine learners. They are also very widely used in a domain called geostatistics. But in geostatistics, they're called kriging. Has anyone ever heard of kriging? There we go, 2 people. So in geostatistics, the reason they're called kriging, or it's coming from a French mathematician called Materon, who picked up a method that a South African mining engineer called Krige, I guess it's an Afrikaans name or probably Dutch origin, had invented. And so he refers to the methodology as, I think in French, krigeage or something like that, as in the method that Krige uses for mining, for spatial modeling in mining. Now, the interesting thing about that is when people say they're doing kriging, they are doing Gaussian processes, but the objects they look at in the Gaussian processes are very different. So they look at an object called the variogram, and the way they tend to fit those Gaussian processes is quite different. They don't tend to use maximum likelihood. They often try and fit the variogram to empirical data, but it's the same set of techniques. And the thing I'm really impressed about the community that Nicolas was in is each of their ability to talk the language of these different sub-communities, because everyone uses a different sub-language for the same thing. So when you look in the literature, you will sometimes see the language of kriging or krigging being used to describe this. Anyway, that's sort of by way of introducing Nicolas, who has now moved to Cambridge and works for Second Mind, that's down on Hills Road somewhere. He wrote this cool little simulator. So he has done in the past examples where you make paper helicopters and you drop them to the ground and you do like Bayesian optimization over the format of the helicopter. But because that's not always easy to create, he's written this little simulator, a catapult, and you can run on this simulator any of the techniques we're talking about. You could do Bayesian optimization, you can do emulation, just trying to fit the function. And what I'm going to suggest you do in the lab class is some sensitivity analysis. So you've got these 4 parameters which are associated with the different parts of the catapult. So these mounting points here, how high up and low up here they are. So in fact, x1 is the rotation axis. So how far to the right or left the rotation axis is. Then the x2, the arm stop. This is the arm stop here, because when the catapult flies up, it hits into this object here. So that decides like how far forward the catapult will be when it fires. The spring binding 1, I don't know, I can't remember which is which. That's one of those, the spring binding 1, the other is spring binding 2. And then you can also set the wind. So what the wind's going to do is just adding noise, right? So if you set none on the wind, you just get the deterministic output of the simulation. And if you click the action, then it does a little picture. You can see the trajectory. I think also if you just press the action, it'll just show you what the distance was below. So the idea is that you're going to use MuKit to initially do a bit of work to fit the function, get a broad outline fit of the function, and do some sensitivity analysis on this catapult. Now, as I say, you can do all of these labs in Colab. It works really, really well in Colab, apart from when you initially fit the function through integrated variance reduction here, that's really slow for some reason that I can't work out. So you'll find that bit may be better done on a local computer if you can get the notebook running on a local computer. Again, I would advise getting all this going, because if you've got it conveniently in a way that you're happy with, that will make the assessment that you're about to do much, much easier. So what you do in that case is your inputs are these 4 different objects: the rotation axis, the arm stop, location, and the spring binding 1 and the spring binding 2. And then what you want to do is you've got to do an experimental design, right? Because you're now going to try and fit this function everywhere, and then you're going to do sensitivity analysis on it. So last time we talked about experimental design, which is how we get the acquisition to ensure that the function that we're predicting is mapping nicely onto the underlying system. So you can do a few different things for the experimental design. You're going to have to start with a model-free design. So that's just to do the initial function fit before you start sequentially acquiring points. And some of those, they're described in the notes. The model-free ones, we talked about them briefly last time. You can choose any of these: a random design, Latin harping, and sampling. What's sampling? I quite like the word, actually. It sounds like a cool activity. I've been going out sampling. It sounds like something you do in the countryside. Like, oh, because it sounds like rambling, that's why. Yeah. So sampling is when you're rambling and you pick up samples, yeah. Sobel sequences or orthogonal designs. So you start with a model-free design, and then you're going to do a model-based design. And so the thing you're set up to do in the lab is to try, well, actually, sorry, I think it's the other way around in the lab. So you start with uncertainty sampling, which you'll find is very fast even on Colab, and then you try integrated variance reduction. If you remember from last time, integrated variance reduction was this very high intensity process where you're trying to sample across the entire function rather than just optimizing for an individual variance point. And that will then just basically teach you what you're seeing, I think, in that lab class is therefore, with this catapult example, the whole process that I think for me would be the first thing I'm going to try if I'm ever given a simulation. So here's the simulation, right? And I want to start to understand what this simulation is. And what am I going to do? Well, I'm going to start fitting my Gaussian process initially with a model-free design and then with some point acquisition. And then I'm going to start trying to understand the sensitivity of this simulation to some different inputs or outputs. Now, of course, if you know that, I mean, if our simulation was fitting neural networks and trying to get the best test likelihood for the neural network, we might not care about what that function looks like. We'd just go direct for Bayesian optimization. But I'm assuming that you want to do some sort of understanding of what this simulation is, what its weaknesses and strengths are. And so this sort of lab class takes you right through those different aspects. So this is what I got. So I've done this. And you get these sort of different sensitivities where that it turned out that the arm stop was highly sensitive for me. I guess what's that, 0.65, 0.2, 0.1, 0.05. So who can tell me, are these the total effects or are they the Sobel indices of each variable? I don't know, it's quite hard to tell actually, because I can't remember, I haven't labeled it. So they could be either, because the total effects, neither the total effects, well, the total effects, I'm just trying to work that out. In order to compute the total effect of an individual variable, it's recursive to try and compute the Sobel indices, right? So if you want the 7th order effect, you have to have computed the 1st order effect, the 2nd order effect, the 3rd order effect, the 4th order effect, the 5th, and so on up to the 7th order effect, okay? And that's a lot of computation because each of those samples is requiring you to do high dimensional, a number of Monte Carlo integrals. When you're computing the total effect of a variable, though, you don't have to do that because you know the total variance. So you can start with the total variance and remove the effects of the other variables. So that's a really important trick, why we can compute the total effect. And if I want to compute high order effects without the total effect, it requires a lot of computation. So it looks like one of those plots will be in the total effect. And that's what we can see now, because this effect is only going up to 0.64. And then, so that must be the Sobel index for the arm stop. And then the total effect is a little bit higher, right? We've gained a little bit in this second plot. Because these effects can never be, oh no, now I'm, Monte Carlo sampling. Seems basically that we might have an error between the Monte Carlo sampling between that and the next, because that should be the total effect. Okay, so I stop there, and then, you know, we've got a lot of time today for going through questions or things like other lectures. We've been a bit cut short on that and had sort of get thrown out. So I wanted to make sure that we got more time to talk about this and anything else you're curious about. Next lecture will be multi-fidelity. So that's the case where you've got different simulations of different levels of fidelity, and we're going to want to try and combine them. So that's like the most sophisticated thing